Hi, welcome to another week of our Chem 1212 lab here at North Georgia. I'm Dr. Meyer again. What we're going to be taking a look at this week is something called Beer's Law, which is maybe something a little unusual from what you're used to in lecture. And really what it's going to deal with is looking at something called the absorbance of a particular solution and trying to figure out really kind of where does a particular solution or a particular compound absorb best at, and trying to use that information then also help us figure out unknown concentrations. So Beer's Law itself really deals with the fact that the absorbance of a solution is directly related or linearly related to its concentration. And so we're trying to take advantage of that fact to help us kind of really figure out unknown concentrations is kind of the usual goal. Although in this experiment, we're actually going to do something a little bit different, and that's actually going to let us help figure out some kinetics information for the next lab that's going to look at lab 5 that's going to take a look at kinetics as well. So our starting point for this experiment, we have kind of 3 major parts. I'm going to kind of go through and kind of step up to kind of some of the setup here that I have to kind of explain each one. The first part is really going to be a simple dilution. So we're given a really concentrated solution of crystal violet to start out. And by really concentrated, it's really only 1.0 times 10 to the minus 4th molar. But it's a crystal violet dye that's extremely intense. And for us to measure absorbance kind of accurately and get data that's worth using, we usually want our absorbance to be a little bit on the lower side. The more intensely colored something is like this, where light's having a hard time passing through the solution, the less useful that's going to be from kind of an actual data standpoint for what we want to be able to do for this experiment. So we're going to dilute the solution down as kind of the first part of the experiment. And then our goal is we're going to use kind of what's called a spectrophotometer, which is kind of the little device setup that I have kind of set up here, to try and measure the actual absorbance of our solution over a bunch of different wavelengths. And I'm going to get to kind of a different view here. So this thing's set up to measure absorbance, it kind of knows that. And basically the way this is going to work is we're going to take a little cuvette, and this one just has water in it right now. It's kind of a sample. Basically we can put our little cuvette in here. It's going to shine light through the cuvette, and it's going to measure kind of how much light it's shining at the beginning and how much light passes through the whole solution and gets to our detector. And by measuring how much basically doesn't make it, we can relate that then to what we call absorbance to figure out how much light our solution is absorbing, and then eventually relate that to our concentration. In the case of the water that I have over here, we'll use that as a blank when we get ready to do our first scans, and we'll get to that here very shortly. But before we actually go to do any of the measurement portion with our spectrophotometer, our starting point is actually going to be doing that dilution so that our solution that we want to use for a crystal violet is not so intensely dark that the light doesn't really pass through it at all. That wouldn't be useful to us in terms of actually trying to relate concentration and absorbance for this compound, because it does have a really high what's called molar absorptivity. It absorbs a lot of light in the areas that it does absorb light. Now, to do our first step, just doing a kind of a simple dilution, the concentration that we're given here is a stock solution. This is about 1.0 times 10 to the minus 4th molar that I mentioned before. What we want it to be is 2.5 times 10 to the minus 5th molar. So basically a fourth of the current concentration. And if you're trying to remember, well, how do I figure out how to do a dilution? You can use an M1V1 equals M2V2 equation. I have kind of some of the calculations here that I'll go over at the very end of the lab to kind of refresh people on when I kind of present all the data. But basically, it's kind of it's a 1 to 4 dilution. If I'm at 1.0 to the minus 4th right now, I want to get to 2.5 to the minus 5th, so it's 1/4 the concentration. I basically need to quadruple my volume to get my concentration to go down by a factor of 4. So to do that, all I'm going to do is basically take it, and the lab tells us we're going to take 5 milliliters of our crystal violet solution, and then we want to basically end up with a solution that's 20 milliliters in order for us to end up with the concentration we want. But that 20 milliliters does already include the 5 milliliters of our stock solution that we start with. So how I'm going to be measuring things out, this is how we basically make all the measurements in this lab. We're going to be using these little syringes, which have nice little markings on them that go up to a maximum of about 1 milliliter. I'm trying to get a reasonably accurate measurement here. And I'm kind of actually going by where the actual liquid level is in here. There's a tiny little air bubble. That's not that big a deal because we see kind of exactly where the liquid's at. And I have the liquid actually kind of at the actual maximum right now. It's actually maybe just a touch over, so I can actually get rid of just a tiny bit to get to exactly 1 milliliter of my liquid that's basically in the syringe. And I can go ahead and add this to this beaker that I'm going to actually create my solution in. And I'm basically just going to do this 5 times to get my 5 milliliters. So I'm going to do this real quick so that I have all of the crystal violet that I need. And then I will go back and I will add water to this. Just trying to make sure I get reasonably consistent, accurate measurements for this. So this will be my 2nd milliliter. And for this crystal violet solution, you do want to be a little bit careful in handling it. It's not going to cause any kind of like long-term harm or damage to your skin, but it will stain your skin and it will stay stained for a while. And so unless you want like purple streaks on your skin, you do want to be at least a little cautious as you're handling it. It's going to be my 3rd milliliter. So do this 2 more times. And then since I want my total volume to be 20 milliliters, that means I am going to need 15 milliliters of water. And I've conveniently kind of already measured that out in a graduated cylinder. And this is something I do want to point out because I know a lot of people do this lab. They just want to use, like you're given a bunch of small beakers, like I have a small beaker here of water, and they'll like just measure between the 15 and 20, like, oh, that's 15. It's like, well, that's not really accurate enough. Also, the markings on beakers usually aren't very accurate for their volumes. And so you're much better off actually using a graduated cylinder to make your measurement. And we're almost, this should be the last of my crystal violet solution that I need. So now I have my 5 milliliters for my crystal violet solution. And now what I'm going to do is to get my dilution, I'm going to go ahead and add, this is 15 milliliters of water that I've already pre-measured out in a graduated cylinder. And so I'm going to go ahead and just mix those together. And now what I have is a stock solution that I can use to actually do the first part of this experiment, which is going to be trying to measure the absorbance of this solution, which notice it's not quite as dark in color as my original one was. It is a little bit lighter, and that's a good thing. So hopefully light can still pass through this, although it might not be a whole lot. But then some of the later experiments we're going to be doing, we're going to be cutting that concentration down even more. And eventually the last part, we'll actually look at doing a reaction with this compound to kind of see how that, and we can measure the absorbance over time to measure reaction progress, which again is kind of a nice application of Beer's law. So in terms of setup for our spectrophotometer and using our spectrophotometer, a couple things here. When you first plug in our spectrophotometer here to a LabQuest, you should see a menu that pops up with a little red box that says like USB and absorbance. If it doesn't happen, we'll probably have to get you a different spectrophotometer or a different LabQuest because there are sometimes some communication issues between them, unfortunately. But in this case, it's working fine, ready to go. It's already set up to do a full spectrum. And by a full spectrum, basically, it's going to scan at every wavelength in the visible spectrum and basically just see like where does it absorb. So for me to do this, and actually I don't have my play button showing up down here, so I can just tell it to play with the little button that's here. And the first thing it's going to want to do is take a blank. And so it says it wants to take a blank, but it has to warm up the lamp. So it's going to take about 90 seconds for that to warm up. And while that warms up, I'm going to go ahead and get my next sample ready in a new cuvette for my actual sample. And these cuvettes, just to kind of give you kind of a quick view of these, the ones we normally use have kind of a little slit in the side where you can kind of view through. That's where the light needs to pass through. And if you actually look, the top of them usually have kind of like a little almost kind of like carrot or a little triangle kind of going down. Basically, you want to line this triangle up with, there's a little triangle that right here in the spectrophotometer showing that the light passes this way through it. And so you just want to line it up so the light's going to pass through that little slit. And so I'm going to go grab a syringe here real quick while this thing warms up. Then we'll go ahead and fill up our cuvette, and we'll go ahead and get started with the experiment. All right, so I have my syringe. I'm going to go ahead and for filling up the cuvettes, the only thing you really have to look out for is you really just want them above kind of where your slits are, just so that there's enough in there that it covers all the area where the light's really going to be passing through. So there's not a definitive specific volume you have to have. It's probably going to be somewhere between 2 and 3 milliliters should be plenty. So like 1 milliliter almost filled what I need right there. I can probably just do a 2nd milliliter and that should be plenty for what I'll need for my measurements. And so notice I don't have the cuvette filled all the way to the very tip top. That's fine. Everything of where the measurement's going to be made is already covered, so I don't really need to worry about adding more. Now, I do, if I wanted to be really careful with this, if you want to avoid getting fingerprints on it, like I might have just a second ago, we do have things called Kim wipes that we can use to wipe these off. Unfortunately, actually, I do still have some left. And so we can use a Kim wipe. It's usually better than a paper towel. It's not at a risk to scratch these, although the cuvettes we typically use for this experiment aren't the most expensive ones. There are definitely more expensive ones out there than what we're using. I can just take it with a cuvette and make sure I don't have any fingerprint oils on the bottom part of this cuvette in particular, where the light's going to be passing through and we're going to be making our measurements. All right, at this point, my 90 seconds should have passed. And so my LabQuest is now telling me the warm-up's complete, so I can now tell it to finish the calibration with my blank sample, which is just the water. If you're using a different solvent than water, you would just want a blank cuvette with, or basically a cuvette filled with whatever your solvent is for your solution. And now it says that it's completed my calibration, so I can tell it to just, that's okay, should be ready. And now what it's going to do is it's actually going to start scanning. And I'm going to get basically a scan that looks like it should hopefully be relatively empty. That's fine. And now what I want to do, if I actually want to make measurements, I can go ahead and take this sample out. I can actually tell this to stop for a second. I can take my blank out, and now I can go ahead and put my actual sample in. And again, if I want to make sure it's oriented correctly, I can look for, here's my little triangle sign. I can match it up with the triangle here that's on my spectrophotometer, make sure the light's going to pass the right direction. I'm going to tell this to play. And now what it's going to do is it's going to generate this plot. And it looks really colorful here, and I can adjust the wavelengths. I want to look at this actually went a little bit past the visible spectrum, and I'll move this up a little bit so it can hopefully be seen by our camera a little bit better. But we see a really big peak in here, what looks like kind of the yellow region of our spectrum, which is pretty much what we would expect. And so I'm going to go ahead and stop this. And what we want to really figure out from this, we want this plot, and I'll have this plot in the data that's kind of going to come out with this experiment, so that you can kind of plot everything and find your exact lambda max and kind of show the image of where your lambda max is coming from for your data workup for the post lab. But what we want to do is basically look at and pick out where is the highest absorbance on the graph that we're looking at, or on this plot that we're looking at here, where it's basically telling us the absorbance over these different wavelengths. And usually it's somewhere around 585 to 590 nanometers for the units. So that's what I'm looking for. In this particular case, if I actually look at this one, where my maximum's at, if I kind of try to get to where I think it is, and it looks like for this one, it's about 589.6 is what I'm getting. So I'm going to write that down as a lambda max, 589.60 nanometers. And now when I go to my second part of the experiment, I want to remember that value, because if that's where our crystal violet dye absorbs like the best, that's where we want to be looking when we measure the absorbance for future solutions, where we're going to vary the concentration and look at how that absorbance actually changes with concentration. So that's going to be the second part of our experiment that we're going to move into next. All right, so for the second part of this experiment, what we're going to be doing is making kind of just a bunch of different concentrations and basically just measuring their absorbance. So I have made one kind of change to the LabQuest settings, which the camera may be able to see from here decently or not. I'm not 100% sure on the glares. But if I'm looking at this, it's telling me now it's actually giving me an absorbance reading. What I did to do that, in this upper right-hand corner, I changed it from full spectrum to time-based. So instead of seeing that plot with kind of some of the colors and stuff on it before, now it's just telling me what the absorbance is. And I also, when I hit this little red box, I get an option to change the wavelength. I just set the wavelength to whatever my lambda max was from the first part of the experiment. So I'm using those results from part 1 to help set up for part 2. And now I'm just going to be measuring the absorbance of some different concentrations. And so the first one that I'm actually going to start with the most concentrated. So basically I'm just using my actual stock solution here. So I'm just going to take some of our stock solution that we created for part 1. I'm just going to add this to our cuvette. And we're just going to go ahead and measure this thing's absorbance to see what is the absorbance at our lambda max approximately. And so if I go ahead and add this to my spectrophotometer and measure our absorbance, I'm getting something right about 1.4, looks like about 1.45 something. It's bouncing around quite a bit, so I'm going to give it a second to kind of stabilize. Now that it's getting a chance to kind of slow down, it's bouncing around a little bit. Looks like it's settling in about 1.456 roughly. That last decimal, it's not the end of the world if we get it perfectly accurate. It's kind of our estimation in terms of like sig figs and things like that anyway. So not really that big of a deal if it continues to bounce around. So I'm going to write this down as 1.456 for my absorbance. And now what I'm going to do is I'm just going to do kind of the same idea, but I'm just going to be making different concentrations to measure the absorbance up. So I'm going to pour out my stock solution from here. And if we had an unlimited number of cuvettes and supplies, we would probably get a new cuvette for each trial of this, since I'm going to be changing concentrations. But since we don't have an infinite number of cuvettes and supplies, we are just going to reuse the same one, just kind of rinsing it out each time. Ideally, I would like to get all the water out of this, because any water that's still left in the actual cuvette might dilute whatever sample I put in there next, so that we get a lower absorbance than maybe what we expect. Hopefully we won't see too many side effects from that as we go. We shouldn't see anything too terrible. All right, so the next solution I'm going to make, I'm just going to kind of work my way down the list. Next concentration was 1.75 to the minus 5 molar. If we do our kind of calculations for this dilution, turns out I should need about 2.1 milliliters of my stock solution, the crystal violet. And I need my total volume to be 3 milliliters, which is kind of what's happening for the calculations for all of these for this part of the experiment. Our final volume is 3 milliliters, just because about 3 milliliters is enough to basically run 2 samples in your cuvette if you really need to. And so already got 2 milliliters, now I just need the 0.1. Just my 0.1. And then I need about 0.9 milliliters of water. So looking at this, there's about 0.9 mils of water. And once I have all of that added and I start mixing it up some, what I'm going to do is now I'm just going to take some of this and I'm going to add to my cuvette that I just rinsed out, and I'm going to measure what my absorbance has now become. So I can go ahead and take a look and make sure I have it lined up properly. Put it in, look at my spectrophotometer. Looks like I get an absorbance of about 1.1, around 1.129 or 1.130. Looks about 1.1, probably 2 something is where it's closer to now. It's kind of been bouncing around some, so I'm going to give it a second to kind of stabilize. And it's back up to that 1.129, so I'm just going to go with what that said originally. So 1.129. So that's my absorbance for the second one. And what I'm going to do, rather than make you sit here and just watch me kind of painfully measure out each one, I'm basically going to repeat this for the rest of our concentrations, just writing down the absorbance. And that's all we're doing for the whole second part of this experiment. I'm just writing down these absorbance values. And what I'll do kind of at basically the end of the lab, I'll have kind of an actual table of data that I'll kind of show to everyone and record, so you can actually see all the data that you're going to be getting and see those measurements that you're going to need to get your calibration curve. Because the purpose of this data that I'm getting right now is by measuring the absorbance at different concentrations, I'm generating what's called a calibration curve, so that now when I do my last part of the reaction, or my last part of the experiment, which is going to be an actual chemical reaction between the crystal violet and sodium hydroxide, that I can then kind of monitor what is the concentration of the crystal violet over time. That's kind of what I want to be able to do at the end of everything. And so this is just the calibration curve to help me convert absorbance to concentration, so that when I make these same measurements during my reaction, it's going to be measuring absorbance values, but I can just convert all of those to concentrations. And now I have a way to look at how my concentration is changing with time. And that will basically be kind of the preface to our kinetics lab, lab 5, which is basically going to be that same crystal violet sodium hydroxide reaction, and investigating the kinetics of that reaction to see what the reaction orders are for our different reactants and things of that nature. So I'm not, like I said, rather than show you all the, like I said, the painstaking just making the measurements, I'll kind of summarize all of that towards the end. I'm going to jump to kind of the third part of the experiment next, where I'm actually going to set up that reaction. Right, so for the last part of our experiment now, I'm going to do just a reaction between our crystal violet and sodium hydroxide, which really just kind of amounts to an acid-base reaction. Our crystal violet actually is kind of a weak acid, and once that crystal violet is neutralized and it's no longer acidic, it actually loses all of its color. And so this last part of our experiment, we actually get to do a chemical reaction where we're going to react our crystal violet, our last bits of our stock solution that we made, and we should actually see its color dissipate over time as it reacts with the sodium hydroxide. So I'm going to mix things in this beaker, and what I'm going to do is immediately take the stuff out of this beaker and go ahead and add it back to our cuvette that we're going to run our experiment in. And what I'm going to do here is for my reaction, I'm going to go ahead and measure out all of my crystal violet first. I think it wants us to use about 5 milliliters of our solution, which I should have just enough for that stuff to do that reaction. So measure this out pretty quickly. There's 2. And if we had a graduated cylinder at this point, we could use the graduated cylinder. Since 5 milliliters is definitely big enough volume for a graduated cylinder, there's 3. 4 milliliters, and 1 more. There's 5. All right, so there's our crystal violet stock solution initially. And now what I'm going to do is I'm going to add 1 milliliter of this is 0.1 molar, actually make sure I'm going to add the right thing, that would just be water. 0.1 molar sodium hydroxide. I'm just going to add 1 milliliter of this. And the biggest thing we're going to take note of here is just what is our color of this initially, and where is it going to end up kind of at 10 minutes. And so I'm not gonna make the video just basically sit there and watch absorbance recordings for 10 minutes. But what I'm gonna do before I actually add this, I'm gonna get my spectrophotometer setup ready to go. And for my spectrophotometer, the only thing I'm gonna have to adjust from what I was doing in the previous part is I just need to change the duration that it's set to record for. So CSE Pub wants us to give 10 minutes worth of data. So I'm gonna set a duration of 600 seconds. Say done, okay. And now it's ready to start measuring the absorbance basically whenever I put things in there. And it's gonna measure the absorbance over a 10-minute interval, and I should see that basically our absorbance constantly decreasing, because as our crystal violet reacts, it's gonna start losing its color. And so it's gonna lose some of that color intensity because there's less and less crystal violet there that has that color that's absorbing the light. And so we should be able to monitor the progress of our reaction as we see that basically the absorbance value drop over time. So I'm gonna go ahead and add my 1 milliliter sodium hydroxide to this. And at this point, I can go ahead and mix this a little bit just to get it kind of started. I'm gonna take my cuvette that I intended to use for my reaction here. And I'm gonna go ahead and put some of this into the cuvette so we can measure this in real time. And ideally, we kind of get the early part of this reaction where we can see it really well. It doesn't really make that big of a difference how long it takes to get this in there. But at this point, when I have this ready to go, I can go ahead and make sure, again, just make sure the slit's lined up properly. I can see my absorbance value. It's actually a little bit less than what my stock was originally. It's a good thing. And we should hopefully start to see this decrease over time. I am gonna go ahead and hit play here on this thing just to start recording. And I'm just basically gonna let this go for 10 minutes. And again, like I said, I'm not gonna make you watch the whole 10 minutes, but what I am gonna do is the next clip kind of the video that we're gonna look at, I'll give you kind of a view of what this thing looks like for its color. Remember, it started out looking like this in terms of like its actual darkness. And so I'll compare to this at the end of our 10 minutes so that you can see like what does it actually look like. And then I'll present at that point a lot of the data that you're gonna need. And I'll basically probably show just in an Excel spreadsheet form that you're likely to get the file in so you kind of know what you're gonna be doing for the calculations. But that pretty much should be it from the experiment standpoint. The last bits, I'll just kind of mention some cleanup things. All of our crystal violet gets collected kind of all together, so all of our waste at the end. And we do have our basically just a waste container typically in the hood for this experiment where all of this goes into the waste. None of it can really go down the sink. If you just have like a beaker of water, obviously it's fine to go down the sink, but the crystal violet itself can't. So we need to specially collect all of that for waste disposal. But other than that, there's not much else for this in terms of experiment setup wise. I will show you, like I said, just visually what the kind of color looks like at the end of our 10 minutes. But then after that, I'll talk about some data stuff, and that'll be it for this experiment. Right, so this last little part here, and I apologize for any wobbliness in the camera. Basically what I just wanted to show here is like if we're looking at our cuvette that we started our reaction with, remember it started out the color of that beaker behind me. And after our reaction's done, after a little more than 10 minutes have passed at this point, basically our cuvette's gone clear, which just shows that pretty much all of our crystal violet has reacted in this case, which should be expected. It actually is not the limiting reagent. Given enough time, it should pretty much all react and go away. And we see there kind of a quick plot. Actually, it looks a lot better when I put it in Excel in terms of, if it's a straight line or a curve. It actually should be a slight curve. Actually, if I chop off about the first 20 seconds of data where I was kind of like jostling and kind of putting the cuvette in correctly, then really the data actually looks pretty good. It has kind of a nice little general curve, and you'll see that in the Excel file that I send out here in a little bit as well. But I just wanted to kind of demonstrate there that after our 10 minutes, when our reaction's done, we do see a pretty stark color change, which is what we kind of expect in this case. We're gonna have one last little clip that I'll kind of pair with this as well. That's gonna be taking a look at Excel and showing you guys kind of all the data that you're gonna be getting and kind of what you're gonna be doing with it. All right, so instead I wanted to just show a little bit with the Excel data here in terms of like what you're actually gonna be getting. And so this is actually all the data that you're going to get in an Excel file. You're basically getting the file as is, as you see it right here. And so you have all of your data from part one, which basically has wavelength and absorbance values. So this is kind of like that little curve you saw in part one that you can use to find lambda max. So you can kind of basically sort through here on your wavelengths and figure out like where is the biggest absorbance value, and that is your lambda max that you want to record for the experiment. These are all of your concentration and absorbance values for part two, so the different concentrations of our solutions and the resulting absorbances of each of them, or absorbances. And what you can do with that is you're going to basically take this data and you're going to plot it, and you should get hopefully what looks like pretty close to a straight line. And if you've done it right with the right units, which pretty much it's already set up for, then you should be able to get a slope of that line that tells you your molar absorptivity. And that's kind of your end goal of what you're trying to find here. Because you can use that molar absorptivity to help basically change the data that you have here for part three, where instead of having it just be time and absorbance, you can actually have a time versus concentration instead. And again, concentration versus time is the relationship we look at for kinetics. And by looking into kind of like how those kind of compare in this experiment, hopefully when we get to the kinetics lab, it'll make more sense about how we can get away kind of with using absorbance versus time in the plots there rather than having to do concentration, even though technically kinetics is all about concentration versus time data. But that's really it for this experiment. You guys are going to get this basically exact Excel file you see right here to kind of help you do all of the post-lab calculations. Hopefully that kind of covers all the major details that you need. And if you do run into any issues, please reach out to your instructors or myself, Dr. Meyer. We'll be happy to kind of help you as needed.